All right, so for our final lesson on reflective geometrical optics and the law of reflection, we're going to talk about the lens equation for a spherical mirror. So why do we call it a lens equation? Because there's a focusing that's going on here, right? Just to remind you, if I have an object, right, of height HO, we'll call that the object's height, and it's going to be at a distance from the pole, P, of we'll call it DO for object distance. What's going to happen here? Well, let's see where the image is going to form. Let's construct a parallel ray. A ray parallel to the optic axis anyways. Like so, and we know that's going to pass through the focus. Let's also consider a ray that passes, that reflects at the pole. And that under the law of reflection not the best drawn bisector there. Penciling the optic axis again, about like that. Right, so this angle and this angle are the same under the law of reflection. This point here will be the image plane, and I will get an object that has the image height, HI. And it will be a distance from the pole, DI. So I'm going to label some points here. I'm going to call this point I1 and the bottom here I2. So what I'm looking for are some similar triangles. And so right off the top of my head I see a triangle. Let's write it like this. Triangle O, I1, I2. Here to here to here. You see that triangle? It's got this angle theta r in it. And I also have how am I going to label that other point? Yes. So I need to call this O1, object 1, and O2. These 2 points here at the head and the tail of the object. So we'll have a triangle O. Oh, sorry, that's supposed to be a P. That's why I'm confused. So P, O1, O2. Because these angles are the same, these triangles are similar. So I guess I should have drawn it like this. Similar to P, O1, O2. And what does that tell us? That tells us that HI over HO, this distance over this distance, will be the same as the distance from P to O2, which is the object distance, HI over HO will be the same as the distance from P to I1, which we call D sub I, the image distance, over the object distance from P to O2, which is DO. Okay, well that's useful. But we need to find another triangle in here. And if we observe that this angle here is the same as this angle here, as they are opposite angles, and we note that this distance here is HO, approximately, right? So this is for rays that are very close to the optic axis so that the curvature here is not as extreme as I've drawn it, so that we can approximate this little arc length section here as HO. So now we're going to consider the triangle F, I1, I2. So that is similar to, I need to label this point right here, which I'm going to just call it alpha, just because we need a name for it. This is similar to F alpha P. Okay? So what does that mean? Well, that means that the distance HI over HO, the ratio of these two, this height to this height, is the ratio of this distance, which is the point I1 minus F. Well, really it's DI minus the focal length, which I'll write in here. That's another distance that we needed, the focal length, F. So from this point I1 to the point F, that distance is DI minus F. DI minus F over the distance F. So now I have two expressions for the ratio of the image height to the object height. I can set those equal to each other. So I would say that DI over DO is equal to DI minus F divided by F. Now I can multiply both sides by F and also DO to get that DI times F is equal to DI times DO minus F times DO. And now I'd like to divide everything. So I want to divide everything by F DI DO. And in doing so, when I divide DIF by F DI DO, the DI and the F cancel. I'm left with just 1 over DO. And that's equal to, I can divide this term by F DI DO, and it will only leave F in the denominator. 1 over F minus the last term, F DO. If I divide that by F DI DO, I'm left with just 1 over DI. And if we rearrange that a little bit and solve for 1 over F, this gives us the lens equation, which is 1 over F is equal to 1 over the object distance plus 1 over the image distance. And so typically you'll be given the focal length of the lens, or you'll know it, and you'll know the object distance, the distance of the object from the spherical mirror. And you can use that to determine where the image distance is going to be. However, I should point out that there's a sign convention that we use that's a little bit strange. You have to consider the positive x direction to be in the direction of incident rays. So in this picture here, this would be the positive x direction, which means that all of these numbers here, DO and DI, would both be negative numbers. The positive numbers would be over here. This, of course, would be the positive. Above the optic axis would be a positive number, and below the optic axis would be a negative number, but we don't really need to use that. I think that's all that I wanted to say about the sign convention. It can be confusing, though. Just remember that the direction of the incident rays is the direction of the positive x-axis, which means that in this particular picture, these distances are all negative. Last thing I wanted to mention was the magnification. Well, the magnification is just the ratio of the image height to the object height, which you can see from this first part here is also equal to the ratio of the image distance to the object distance. So if the image distance was, say, 1, DI equals 1, and DO was equal to 2, then the magnification M would be DI, well really it's HI over HO, which is equal to DI over DO, which in this case is equal to 1/2. So that would demagnify. It would be reduced by a factor of 1/2. Whether the image is inverted or not, you will know based on the sign of DI. If DI is positive, it would be a virtual image over here. So that's what you'd get if you were considering, say, a convex spherical mirror. which this works for. Yeah, I think that's all that I have to say about the lens equation. There are many problems that you can work with it, but they're all kind of the same variety. And the only difficult thing is solving for DI. Okay, next time we'll move on to refraction, which is the bending of light as it passes through an optical material like glass, from air to glass.